Hello everyone, I'm going to talk about our work, a conflict-free redactable blockchain. We all know the importance of the immutability provided by the blockchain. Immutability means that no one can modify the content without being noticed, and it helps blockchain provide foundations for many applications. However, it also brings three problems. First, the privacy law adopted by European state, General Data Protection Regulation, grants everyone the right to be forgotten. But it is impossible to remove any data from most of the current blockchain system. Second, everyone has a right to write on a permissionless blockchain, but it has been misused by malicious users. They write illegal or harmful content on Bitcoin, and anyone who wants to maintain the entire history of the system has to store this harmful content. Third, the smart contract is an important application of blockchain. Amending smart contract and patching those codes will be easier if the underlying blockchain can be reducted. So, designing an efficient and secure blockchain that can be modified under controlled conditions is desired. In the work from Dober et al., they constructed a redactable blockchain based on proof of work. After the user submits a request, the leader of each round adds the hash of the request to the newly minted block if he supports the reduction. And if there are enough round leaders who vote for the reduction during a voting period lasting L block, the reduction is accepted and will be performed. A reduction needs to collect enough votes to be accepted, meaning more than the maximum number of votes an adversary can generate during the voting period. That is, more than the maximum number of blocks the adversary can generate among L adjacent blocks. This makes sure that no adversary can modify the blockchain arbitrarily. However, their work suffers from two drawbacks. The first one is that the L block long voting period makes the processing of reduction slow. It takes a few minutes to create a new block in proof-of-work-based blockchain. A voting period of L block can last for days. Second, such a design would break the consistency, cause different honest party to own different blockchain. Now we explain this in detail. Suppose there are two reduction requests for the same block that are proposed at almost the same time. Therefore, their voting period overlaps. During this period, let's assume that half of honest party vote for the first request and the other half vote for the second one. The block generated by the adversary contains the hash of both requests, so vote for both of them at the same time. As we can see, both requests receive more votes than the adversary can generate. Both versions of block reduction are valid. Therefore, our works have three purposes. First, to improve the processing speed of the reduction request. Second, our protocol can properly handle the situation that can cause conflict. Third, the processing of reduction requests will not bring additional burden to processing of transactions. The following presentation consists of three parts. First, basis. To help all parties to reach an agreement on an operation facing a fully adapted adversary, we present our protocol use Byzantine Agreement Protocol from Algorand as a foundation and extend the immutable blockchain allow operations. In Algorand, they design a multi-value Byzantine Agreement Protocol where each step is performed by a new randomly selected party, and a certificate is generated at the end of the protocol so that the results are publicly verifiable. The block in our system consists of 5 parts. A timestamp, which is a round indicator, the hash of previous block data, the validity or proof of the block. These 4 parts are the same as the block in the immutable blockchain, and addition part, IB, represent the original state of the block, that is, the state before any reduction happens. Since only the round indicator and the data are allowed to be modified, the original state of the block is the hash of the round indicator and the data. B subscript L plus 1 extend B subscript L. No modification occurs now, and the two blocks are linked properly. When B subscript L is modified, the original round indicator is changed to the round when the reduction is proposed. The original date is also modified. Therefore, the hash of the previous block, H subscript L plus 1, cannot be verified by the same way. But we keep the original state IB subscript L. So, H subscript L plus 1 can be easily computed with IB subscript L. So the link between these two blocks can still be checked after reduction. Next, I would like to talk about the construction of our protocol. We need a policy that clarifies what reductions are eligible to be voted on. It depends on the application scenario. Most basically, the validity proof for other reduction cannot be delayed or modified. In our system, there are 4 steps for a block to be modified. The user needs to submit the reduction request first. Then, this request needs to be checked for eligibility to be voted on. And third, parties pack and agree on conflict-free request sets. All parties run the consensus protocol and reach an agreement on the reduction request. Extend the blockchain in almost the same way in immutable blockchain is the last step. First, the submission of reduction request. Any user who wants to redact the blockchain gossips a candidate block with an reduction request include a hash of candidate block. Then we check the eligibility of the block. We need the party to check whether the block complies with the policy and whether the block is correctly linked with the adjacent block. If it is, the parties store the candidate block for later processing. The third step is pack all the requests in the current system as a whole for processing. The party in the system need to reach an agreement on this set. And now the Byzantine Agreement Protocol is called from Algorand. Recall that each step of Byzantine Agreement Protocol from Algorand need to randomly select new parties to perform the protocol. And this selection will be different in proof of work setting and proof of stake setting, of course. Let's see how to select first. In proof of stake setting, we can use a similar selection method from Algorand. Each party is required to compute a verifiable random function with its own private key, the indicator of current round, and a seed deriving from the underlying blockchain's input. A party whose result is smaller than a predefined threshold is one of the potential proposers. And each party, if selected, publishes the verifiable result with its proposal. Among all the potential proposers, the proposer of this round is the party with the smallest result. In the following steps, each party also needs to compute the verifiable random function to check whether he is selected to join the committees that perform the protocol. And a step indicator is added as an input of the function. Each selected party uses a proposal received from the proposer in his opinion as initial value. This is the same as in Algorand. In proof of work setting, both proposal selection and commit member selection need to be implemented in a proof of work-based way, of course. However, therefore, we require each party to compute proof of work puzzle and publish the answer, the nonce, as the proof being selected. Now we have ways to select party to execute the protocol for each step, and now when a party is selected as potential proposer, the party needs to compute a conflict-free set as its own proposal and broadcast this set with its selected certificate. And how to compute this set? For each block on the chain, we require that the set contains at most one block. The conflict request may be posted by different honest users at the same time and intentionally or by the adversary deliberately. So, if there are more than one request for one block in current system, the party needs to choose one randomly and discuss others. For honest users whose requests are discussed, they need to resubmit new requests based on the latest modified state, the state that have been approved. Next, as described above, the party will check whether he is selected as a committee member at each step, and if so, if he is selected, he executes the protocol with the same way in Elgrand. At the end, guaranteed by the security of Byzantine agreement, all honest parties will output the same set. Now, at the end of the third step, all requests in the set have been accepted. The party and the user present in the system at the time can accept the result safely. The fourth step is to extend the blockchain. Since we separate the processing of reduction requests from extending of the underlying blockchain, creating new block is similar to that in an immutable blockchain. First, each party needs to update their local chain, then the run leader extends the newly selected optimal chain. The run leader adds the ability proof of the request set into the newly minted block, and the original block is replaced by the candidate block. Finally, he broadcasted the new blockchain. Because the blockchain in our system can be modified, the update of blockchain needs to be slightly adjusted. First, we want to choose the optimal underlying blockchain. Second, to prevent rollback attacks so that the adversary cannot fool the party with old block version and undo any reduction since that version, we want to choose a chain that does not contain outdated redacted block. So we have to compare the run indicator of each redacted block. The run indicator of each redacted block on the received blockchain should be greater than or at least equal to the run indicator of each corresponding block on the local chain. This is the fourth step. We already have mentioned that the requests in the set have been accepted at the end of the third step. By adding the certificate to the new minted block, new party who join the system later can access it easily. Now, let's discuss the confirmation time of the request in our system. Before that, let's see the confirmation time of reduction in previous work. In their work, first, a voting period of L block is required, and then waiting for all blocks containing votes to stabilize in the system. Only when both periods are complete, a reduction is accepted in the system. But in our system, since everyone will have the same output at the end of the Byzantine agreement protocol, there's no need for stabilizing phase. Compared with the previous work, the first voting stage is also greatly shortened, and it only needs to run the Byzantine agreement protocol once. During this presentation, we introduce the basis, the construction, and analyze the confirming time of the reduction. In summary, we extend the immutable blockchain with Elgrand as a foundation to make the blockchain redactable. Compared with previous work, our work has three advantages. First, no addition overhead to the transaction processing. This is because the processing of the reduction is unbound from the extension of the underlying blockchain. Second, no conflict rejections are made to the chain even facing multiple requests for the same block at the same time. And this is achieved by packing multiple requests and processing them as a whole. Third, no wasting time waiting for proof to be confirmed. The party can obtain the decision on the rejection as soon as the maintenance agreement ends. And thank you.